Hey everyone, welcome to The Explainer, proudly made by Forge College. I'm your host, and today we are absolutely tearing into the engineer's blueprint for Web 3. So in our last explainer, we bulletproofed our testing and validating deployment scripts. But let's be honest for a second. Deploying a totally flawless script to a structurally insecure vault is kind of like putting a heavy-duty titanium lock on a flimsy cardboard box. I mean, sure, the lock works perfectly, but literally anyone can just kick the side in. So today, we're making absolutely certain our deposit vaults are structurally sound before we even think about building the exit doors. We're zeroing in on audit-ready deposit patterns and next steps. This is the crucial link between secure deposits and robust withdrawals in applied Solidity development.
All right, let's quickly run through our engineering table of contents for today. We'll kick things off with the secure deposit blueprint. Number 2, spotting vulnerable deposit patterns. 3, the 3 pillars of remediation. 4, building the audit checklist. And finally, number 5, next steps for withdrawals. Let's dive right in.
Section 1, the secure deposit blueprint, securing the vault doors.
Okay, so the core philosophy we're working with here is actually pretty simple, but it is absolutely paramount. You have to solidify your deposits first to reduce the blast radius. Now, what does that actually mean in practice? It means treating your deposit functions as pure, highly verifiable state-updating operations. Basically, in plain English, your deposit function should literally just be doing the math and updating the internal ledger. No reaching out to the chaotic external world of other smart contracts. Think about a traditional bank vault, right? You'd want the internal ledger system that tracks the incoming cash to be completely isolated and flawless before you start hooking up, say, external wire transfers to the whole system. Because if that core bookkeeping is flawlessly contained, well, any future bugs in the much more complex withdrawal phase are going to have a massively reduced blast radius. You're containing the damage before it even happens, effectively building this unshakable foundation for the rest of your architecture.
Moving right along to Section 2, spotting vulnerable deposit patterns, or, what happens when the blueprint completely fails. Picture this, a vulnerable pattern is kind of like a highly distractible bank teller. The teller hands a customer their receipt, turns their back for a split second to put the cash in the vault, and in that exact moment, the customer sneaks a hand back through the deposit slot, grabs more money, and shouts, "Deposit again!" before the teller even has a chance to update the ledger. Now, that sounds totally comical in the physical world, but in smart contracts, this happens at the exact speed of light. And honestly, if your code isn't ready for it, your vault is getting drained.
Let's contrast these two flows. On one hand, we've got the highly vulnerable approach, making an external call out to a user or some other contracts before we even bother updating our internal state ledger. This is the digital equivalent of our distracted bank teller. It's just a classic reentrancy trap waiting to be sprung by a malicious actor. But then, if we flip it to the remediated flow, we do our strict bookkeeping first. We update the state ledger, we do all our internal math, and only then do we make any external calls. Honestly, it's such a simple flip in the sequence of operations, but it's literally the difference between an airtight vault and a catastrophic hack.
Section 3, the 3 pillars of remediation, structural reinforcements. So, we know what structural failure looks like, right? Now, how do we actually reinforce the code? We rely on 3 specific engineering patterns. These are core security concepts that honestly form the absolute bedrock of the learning programs taught over at Forge College. Let's look at the very first pillar.
Pillar number 1 is checks, effects, interactions, or just CEI for short. Think of CEI like a really rigid mechanical gear sequence where one gear absolutely cannot turn before the other. First, you check your inputs. Are the conditions actually met? Second, you apply the effects to your internal state, updating your balances and ledgers. And only third, as the final gear in the sequence, do you interact externally, like transferring tokens. This mechanical step-by-step ordering turns completely ambiguous, risky runtime behavior into rock-solid mathematical invariants. If a hacker tries to re-enter the contract during that external interaction phase, they are going to hit a brick wall because the internal state has already been fully updated to reflect their initial action.
Now, building on CEI, our complete toolkit actually requires 2 more pillars. Pillar 2 is adding reentrancy guards. This is basically snapping a literal cryptographic padlock on the contract so a specific function just cannot be called again while it's still executing its very first run. And then Pillar 3 is the pullover push pattern. So instead of actively pushing Ether out to users, which risks a failed transaction or some malicious fallback function, you simply update their balance and let the users pull their funds whenever they're ready. It completely shifts the risk of execution failure away from the protocol and right on to the user. And when you combine these 3 pillars, CEI, reentrancy guards, and pullover push, you essentially neutralize almost all common deposit and accounting vulnerabilities. It's a real game changer.
Which brings us to Section 4,
Building the audit checklist, the engineer's artifact. This is the moment where all our theory finally meets practice.
So when we build out this checklist, we map a specific code concern, something like, say, an external call before state update, directly to a specific remediation, like apply CEI and a non-reentrant guard. But to leave absolutely zero room for auditor guesswork, we demand a third, absolutely crucial piece, the verification column. Right here is where we document the exact unit tests and static analyzer rules that we use to mathematically prove our fix. You aren't just sitting there telling an auditor the code is safe, you're handing them a highly detailed map with a giant red X on the treasure. You're giving them the exact commands to run so they can verify your claims instantly.
And actually populating that verification column, that requires a very strict mechanical process. First off, run your unit tests locally. Use tools like Hardhat or Foundry to prove that the vulnerable contract actually fails. Because, let's face it, as engineers, we kind of want to see it break first, right? Seeing the exploit succeed in your test environment confirms you actually understand the threat. Then, of course, you prove the remediated one passes. Second step, run a static analyzer, something like Slither, to catch anything you might have missed. And finally, copy those exact rule IDs and test commands right into your CSV. This keeps everything local, it keeps it deterministic, and it proves your blueprint is structurally sound long before the withdrawal team ever even touches it.
And that leads us to Section 5. Next steps for withdrawals. Preparing the exits.
Listen, if you take literally one overarching lesson away from today's explainer, make it this. Explicit verification always beats vague claims. I mean, anybody on the internet can claim their code is secure. Frankly, almost everyone does. But recording the exact test names, the analyzer rules, and having deterministic proof right there in an audit checklist, that is what ensures your audits are completely reproducible, undeniably secure, and actually finally ready for deployment.
So I'm going to leave you with this final lingering thought. Your deposits, they are securely locked in. They are heavily guarded and fully audited. But how on earth are you going to get that ether back out safely? Well, that brings us to our next major challenge, principles of secure withdrawals. To really expand your Web3 engineering toolkit, I highly encourage you to go visit forge.college to learn a whole lot more about this subject and tons of other Web3 related topics. This explainer was made by Forge College. Thanks so much for hanging out with me today, and I'll catch you in the next one.